Look around you right now. Light everywhere. Billions of rays crisscrossing in every direction. When you look at me, someone standing to your left can see someone standing to your right. The light is going this way. The light is going that way. Waves in all directions. And that's just visible light. Right now, radio broadcasts are passing through this room. Television signals. Heat radiation from your body. Radar from airplanes. X-rays from space. All traveling through you. Simultaneously. How does that work? How can billions of light rays go in all directions without everything getting mixed up? How do you see a clear image when this chaos is happening? The answer you learned in school is incomplete, possibly wrong, in ways that matter. The real answer, what light actually is, and how it travels from one place to another, is so strange, so unlike anything in everyday experience, that when you finally understand it, the whole world looks different. Let me show you. Imagine you're sitting by a pool on a summer afternoon. People are diving in. Splash, splash, splash. Kids cannonballing. Adults doing laps. Waves spread across the water. Ripples crossing ripples. Complete chaos. Now imagine a clever insect sitting in the corner of that pool. It can't see. It can only feel the water bump against it. Could that insect figure out what's happening in the pool? Could it tell who jumped in, where they jumped, when they jumped, just from feeling the waves? Sounds impossible. A mess of overlapping ripples, interference patterns, chaos arriving from every direction. But here's the thing. In principle, yes, all that information is in the waves. Every splash, every disturbance leaves its signature. The waves carry the story of what caused them. Position, timing, intensity. It's all encoded in the pattern. Now here's what should blow your mind. That's what your eye is doing right now. The light coming to your eye is waves, except three-dimensional instead of two-dimensional. And instead of water ripples, you've got electromagnetic oscillations propagating through space at 186,000 miles per second. That's about 300,000 kilometers per second. Think about this room. Light bouncing off walls, reflecting off your screen, scattering off dust particles in the air. Waves going this way, that way, every way. A complete mess. And yet, you can sort it out with this little instrument. An 1/8-inch hole at the front of your eye, about 3 millimeters. The pupil. Light enters through that tiny opening. Lens bends it. Retina catches it. And somehow, from this tremendous mess of waves all over space, you extract an image, a coherent picture of the world. You see me. You see the background. You see colors, shapes, depth, motion. All from decoding wave chaos through a hole smaller than a pencil eraser. That's not just impressive. That's borderline miraculous. But that's just visible light, the tiny range of waves your eye happens to detect. Think about those pool waves again. Some are big swells, slow, rolling, long wavelength. Some are tiny ripples, quick, short, high frequency. Turns out your eye only uses waves between certain lengths, about 400 to 700 nanometers. That's roughly 0.0004 to 0.0007 millimeters. Tiny. Incredibly tiny. What about longer waves, the slower swells? Those represent heat, infrared radiation. Pit vipers can see these, pick up mice radiating body heat in complete darkness. Your TV remote uses them. every warm object around you is glowing in infrared right now. You just can't see it. And the waves get much longer. Radio waves, centimeters to meters to kilometers long. Here's the thing that should stop you cold. Radio waves are the same thing as light. Exactly the same kind of wave, same phenomenon, same physics, just stretched out. Right now, sitting where you are, there's Moscow radio broadcasting, signals from Peru, BBC from London, your neighbor's Wi-Fi, radar from airplanes overhead, GPS signals from satellites 12,000 miles up. All passing through you this second. You don't believe it? Pick up a piece of wire connected to a box, a radio. Turn the knobs, and you hear Moscow, or Sao Paulo, or Tokyo. How else did it get there? It was there all the time, passing through the room, passing through your body, invisible. Now go shorter than visible light. Ultraviolet. What gives you sunburn? Your skin detects it, painfully, but your eyes don't see it. Shorter still, X-rays. Pass through flesh, stopped by bone. Same waves, just compressed. Shortest of all, gamma rays. From radioactive decay. From distant exploding stars. Cosmic violence arriving at the speed of light. All the same phenomenon. Electromagnetic waves. Oscillating electric and magnetic fields propagating through space. The only difference is wavelength. And it's all in this room right now. Everybody knows this. But you have to stop and think about it to really get the pleasure, the inconceivable nature of it all. For centuries, people argued about what light really is. Newton said light is made of particles, little bullets shooting through space. Corpuscles, he called them. That's why light travels in straight lines. That's why you can't bend it around corners. Particles fly straight until something stops them. Made sense. Newton was Newton. Case closed. Except Huygens disagreed. Christian Huygens, Dutch physicist. He said light is a wave, like sound, like ripples in water. Waves spread out. Waves interfere with each other. When two waves meet, they can add up or cancel out. That's what waves do. They couldn't both be right, could they? The argument raged for 200 years. 2 centuries of physicists taking sides. Then came the experiment that should have ended it. 1801. Thomas Young. The double-slit experiment. Shine light through 2 narrow slits. 2 tiny openings in a barrier. If light is particles, bullets flying through those slits, what would you see on the screen behind? 2 bright strips, 1 for each slit. Simple. But that's not what happens. You see a pattern, bright bands and dark bands, stripes across the screen. Interference. Exactly what waves do when they overlap. Where wave peaks meet wave peaks, they add up. Bright band, where peaks meet troughs, they cancel out. Dark band. # at META, quote, pause, quote, colon, quote, sex, quote, colon, 1.0. Only waves do this. Particles don't interfere. Bullets don't cancel each other out. Light must be a wave. Case closed. Newton was wrong. Huygens was right. For about 100 years, that was the answer. Light is a wave. Problem solved. Move on. Click, 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 click. Individual arrivals. Detectors catching light one piece at a time. Photons, real particles. You can count them. They make detectors click. They arrive one at a time like bullets hitting a target. Okay, so maybe Newton was right after all. Particles? But wait. Send photons through the double slit one at a time. Slowly. One photon. Wait. Another photon. Wait. Surely a single particle can't interfere with itself. It goes through one slit or the other. How can it make an interference pattern? It does. One photon at a time. And the interference pattern builds up. Each photon seems to go through both slits, like a wave spreading out, exploring all paths. But catch it on the other side? Click. A single arrival, like a bullet. So which is it? Wave or particle? Here's what most people won't tell you. It's neither. Light is not a wave. Light is not a particle. Light is light. We don't have a word for it because we don't have anything like it in everyday experience. We try to describe it using familiar concepts, waves, particles, but those are just approximations, crutches for our imagination. The reality is stranger. Photons are real. You can count them. They make detectors click. But photons don't travel like bullets. They don't follow a single path from A to B. They behave according to quantum mechanics, exploring all possible paths simultaneously, like waves spreading out. When you're not looking, photons explore everything, every possible route. When you detect them, click, a single arrival. Both are real. Both are true. There's no contradiction. Just two aspects of the same quantum reality. Light is light, a quantum object, something we don't have a word for because we evolved to understand rocks and trees and other things we can hold. Light is none of those. Light is something else entirely. So if light isn't particles flying in straight lines, why does it go straight? Why does it bounce off mirrors at equal angles? Why does it bend when entering water? The answer is beautiful and strange. It comes from a principle discovered in the 1650s by Pierre de Fermat. Light takes the path of shortest time. Not shortest distance, shortest time. Think about that for a second. Why does light go straight in air? Because a straight line is the shortest distance between 2 points. And if light travels at constant speed in air, shortest distance means shortest time. Simple enough. But here's where it gets interesting. Why does light bounce off a mirror at equal angles? You shine a flashlight at a mirror. The light comes off at the same angle it went in. Is that the shortest distance from source to mirror to your eye? Yes. You can prove it with geometry. The path where angle equals angle is the shortest total distance. And since light speed is constant in air, shortest distance means shortest time. Now here's where it gets really interesting. What happens when light goes from air into water? Light travels slower in water, about 25% slower. That's roughly 140,000 miles per second instead of 186,000, or about 225,000 kilometers per second instead of 300,000. So now, shortest distance is not the same as shortest time. Here's an analogy. Imagine you're a lifeguard on the beach. Someone's drowning in the water. What's the fastest way to reach them? A straight line? That means swimming more. And you swim slower than you run. The fastest path is to run a bit farther on the sand, where you're fast, and then swim a shorter distance in the water, where you're slow. You trade extra distance on land for less distance in water. The total time is minimized. That's exactly what light does. When light enters water, it bends. It travels farther in the fast medium, air, to spend less time in the slow medium, water. This bending is called refraction, and it's not arbitrary. The exact angle of bending is precisely what minimizes travel time. Mirages on hot roads? Same principle. The air just above hot asphalt is thinner, hotter. Light travels faster in thin air, so light curves through the region where it goes faster, bends upward. You see sky reflected on the road. Your brain interprets that as water. It's not water. It's light taking the path of least time through air of varying density. And here's one that might blow your mind. When you watch the sun setting on the horizon, touching the edge of the earth, the sun is already below the horizon, gone, out of sight. But the atmosphere bends the light, curves it around the earth, so you see a ghost, an image of the sun from where it was about 2 minutes earlier. Every sunset you've ever watched, you were looking at a ghost. Light that left the sun 8 minutes ago, bent by the atmosphere, showing you something that isn't actually there anymore. #Meta. Sex 1.0. All because light takes the path of minimum time. Fermat's principle is beautiful. One simple rule explains reflection, refraction, mirages, sunsets, everything. But here's the uncomfortable question. How does light know which path is fastest? It hasn't tried the other paths. It can't see the future. And yet it always finds the minimum. If this feels like cheating, you're in good company. It bothered physicists for centuries. Before we answer how light knows, let's see what we can do with Fermat's principle. A lens. What does a lens actually do? It makes all paths take the same time. Sex 1.0. Think about it. Light from a distant star hits your telescope. Some rays hit the center of the lens. Some hit the edges. The center rays travel the shortest distance through air. The edge rays travel farther. But glass slows light down. So we make the glass thicker in the middle. Center rays, short air path, long glass path, slowed down. Edge rays, long air path, short glass path, less slowed. Result? All paths take the same time. They all arrive at the focal point simultaneously. That's what a lens is, a device that equalizes travel times. Parabolic mirrors? Same principle. Want to collect starlight from billions of miles away? Shape the mirror so light hitting anywhere on its surface takes the same total time to reach the focal point. That shape is a parabola. Not because parabolas are mathematically pretty, because that's the shape where all paths take equal time. Every telescope, every camera, every pair of glasses works because of Fermat's principle. And here's where it connects to your life right now. This video is traveling to you as light through fiber optic cables under the ocean. Pulses of light carrying data at 186,000 miles per second. That's 300,000 kilometers per second. Crossing continents in milliseconds. Your Wi-Fi router is broadcasting radio waves right now. Same phenomenon as visible light, just different wavelength. Same physics. Remember Interstellar? When Cooper sends messages through the black hole to his daughter across decades of time. That's light, carrying information across space-time. We've been doing that since the first telegraph, since the first fiber optic cable, since the first radio broadcast. Every time you use your phone, stream a video, send a text, you're manipulating the same quantum phenomenon that puzzled Newton and Einstein. Light isn't just something you see. Light is how the universe communicates with itself. And you're using it right now. How does light know which path takes the least time? It hasn't tried the other paths. It can't see the future. And yet it always finds the minimum. Here's Feynman's answer, and it's going to change everything. Light doesn't know. Light tries everything. Every possible path, every crazy detour, every ridiculous zigzag. Light explores all of them simultaneously. This is quantum mechanics, and it's as strange as it sounds. Here's how it works. Imagine light going from point A to point B. In quantum mechanics, light doesn't pick one path. It takes every conceivable path at once. Straight line? Yes. Curved detour through the ceiling? Yes. Bounce off the wall, loop around the moon, come back? Yes. Every path, all at once. But wait. If light takes every path, why does it appear to go straight? Here's the beautiful part. Each path has a clock attached to it, an arrow that spins as the light travels. The longer the path, the more the arrow spins. When light arrives at B, you add up all the arrows from all the paths. Most of them cancel out. The crazy paths? Their arrows point in random directions. They cancel each other. But the paths near the shortest time? Their arrows all point roughly the same direction. They add up. The straight line isn't special because light chose it. It's special because it's the only path that survives the cancellation. This is Feynman's path integral formulation. One of the most profound ideas in physics. Light doesn't know the shortest path. Light explores everything. And the shortest path is what's left after everything else cancels out. Think about what this means. Every photon hitting your eye right now explored every possible route through this room. Bounced off every wall, every surface, every atom. Took paths through the ceiling, through the floor, through dimensions you can't imagine. All those paths interfered, canceled, combined. And what survived? What reached your eye? The paths where the arrows lined up. That's why light goes straight. That's why it bounces at equal angles. That's why it bends in water. Not because it's smart, because everything else destroys itself. If this feels like cheating, if it feels too strange to be true, you're in excellent company. This confused Einstein. He never fully accepted quantum mechanics, called it spooky action at a distance. But Feynman embraced it. He said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." The universe is stranger than we can imagine, and that's okay. We don't have to imagine it. We just have to calculate it. And the calculations work. How do we know light really explores all paths? Because we can force the other paths to contribute. A diffraction grating. Thousands of tiny slits. When light passes through, something strange happens. Instead of going straight, light bends at specific angles. Angles that should be wrong according to Fermat's principle. What's happening? The slits are blocking most paths. Only certain paths get through. And without all the other paths to cancel them, the wrong paths suddenly become visible. You're literally seeing light take paths that aren't the shortest. That's how CDs work. Look at the back of a CD. See those rainbow colors? That's diffraction. Light exploring paths it shouldn't take because the tiny grooves block the normal cancellation. Butterfly wings? Same thing. Those brilliant blues and greens aren't pigment, they're structure. Microscopic patterns that manipulate which paths of light survive cancellation. The butterfly isn't painted blue. The butterfly is shaped to make blue light's paths add up, while other colors cancel out. Holograms? Same principle. A hologram encodes interference patterns, which paths survived and which canceled. Shine light through it, and those paths recreate a 3D image. Every rainbow, every soap bubble, every oil slick on wet pavement, all of them are light-exploring paths, and having most of them cancel out. The colors you see are the paths that survived. And here's the deepest confirmation. Quantum electrodynamics, QED, Feynman's theory. It predicts the magnetic moment of the electron to 12 decimal places. That's like predicting the distance from New York to Los Angeles, accurate to the width of a human hair. No other theory in science is that precise. And it's all based on light exploring every path. This isn't philosophy. This isn't interpretation. This is the most precisely tested theory in human history. Light really does explore everything. The math proves it. The experiments confirm it. That's what light is. Remember those pool waves? Some were big swells, slow, rolling. Some were tiny ripples, quick, short. Light works the same way. The longest waves, meters to kilometers long, are radio waves. AM radio, FM radio, TV broadcasts. Same thing as light, just stretched out. Your car antenna is catching waves that are literally meters long. Shorten the wavelength a bit. Centimeters to millimeters. Microwaves, radar. Your microwave oven works because water molecules absorb electromagnetic waves of certain lengths. Those waves happen to be about 12 centimeters long. That's roughly 5 inches. Same physics as light, just a different wavelength. Shorter still. Infrared. Heat radiation. Everything warm glows in infrared. You're radiating it right now. Pit vipers see this. Pick out mice by their body heat in complete darkness. Then, visible light. The tiny range our eyes happen to detect. About 400 to 700 nanometers. A hair's width divided by 100. Blue is short, around 450 nanometers. Red is long, around 650 nanometers. That's it. The entire rainbow fits in that tiny band. Shorter than blue, ultraviolet. What gives you sunburn? Shorter still, X-rays. Pass through flesh, but stop at bone. Shortest of all, gamma rays. From radioactive decay. From distant exploding stars. All the same phenomenon. Electromagnetic waves. The only difference is wavelength. Radio waves pass through walls because walls are smaller than the wavelength. X-rays pass through flesh because flesh is larger than the wavelength. It's all light, all the same thing. And it's all in this room right now. Right now, sitting where you are, radio signals from thousands of stations are passing through your body. Infrared from everything warm. Visible light bouncing around. Cosmic rays from distant galaxies. All coexisting. All passing through each other without interfering. You're swimming in an ocean of electromagnetic radiation. You just can't see most of it. That tiny slit of visible light, that narrow window your eyes respond to, that's all you get. The rest is invisible. But it's there. All of it. All the time. And it's all the same thing. Just different wavelengths of the same underlying phenomenon. So what is light? Not a wave, not a particle. Light is light. We don't have a word for it because we don't have anything like it in everyday experience. It's a quantum object. When you're not looking, photons explore all paths, interfere with themselves. When you detect them, they arrive as discrete quanta, clicks in a detector. Both are real. Both are true. There's no contradiction. Just two aspects of the same quantum reality. We evolved to understand everyday objects, things we can hold, things that stay where we put them. Light is none of those. Seconds 1.0. Light is something else entirely. But we can understand it by following the mathematics and experiments. And they lead somewhere strange and beautiful. Now here's a thought that should stay with you. Imagine light disappeared from the universe. Not just darkness, that's the least of it. No electromagnetic force means no chemistry. Atoms couldn't form molecules. Stars couldn't shine. Your neurons couldn't fire. Every color, every sight, every warmth you've ever felt, gone. Light isn't just what you see. Light is how the universe communicates with itself. And somehow, through a tiny hole in your head, you get to listen in. Think about what's happening right now. Photons from the sun, infrared from everything warm, radio waves from hundreds of stations, X-rays from space, cosmic rays from distant stars, all passing through the same space at the same time. A tremendous mess of waves. And yet we can sort it out. Tune a radio and hear a single station. Look and see a coherent image. Your eye, that 1/8-inch hole, decoding the chaos of the universe. When you understand what light is, really understand it, the world is far stranger than it appears. Far more beautiful. And that's what physics is about. Expanding our intuitions to grasp nature as it actually is. That's the beauty of it. The terrible, wonderful beauty of understanding. Hey, Meta. Sex 1.0. If this changed how you see light, even a little bit, drop a comment below. Tell me what clicked for you. Subscribe if you want more physics explained the way Feynman would have explained it. No memorization, just understanding. And I'll see you in the next one.